Okay, we start up again with our pendulum. Yes, we can find a driving torque into this problem, but it's not a constant thing. So the question was how to handle it. How should we use bond graph here to easily find a solution? If you forget bond graph for just one moment, it shouldn't be too hard actually to find an expression for this system here. What will we have on the other side? Newtonian mechanics. You have a torque. Well, the torque will actually produce rotation. It will change the spin. So here you will have time derivative of the inertance multiplied with the rotational speed, which then is phi with a dot above. And here, of course, the I is constant. The moment of inertia for a solid object, it doesn't change. And then you will have phi double dot. So this, as you can see, is a differential equation which cannot be solved analytically, at least not easily. Double derivative of function equals a sine of a function. Oh, that's not funny. So this is clearly something we must program. That was the Newtonian mechanics. Okay. How should we do it? Well, instead of using gravity, use a spring. Use a spring instead of gravity. Use a spring. Okay, what was the spring? That was a C element, and when we had this one correctly, we had the effort up here and the flow down here. The effort was then equal to the displacement divided by C. That's sort of a definition of a spring element. So that implies the C. You can also use this one as a definition if you like. C equals Q by the effort E. So there's a connection between displacement and the effort. The displacement in our problem here, that's just the angle phi. But the effort, well, here will be, of course, this torque that we have here. So under here we will have mg L half and then multiplied with sine to the angle phi. So, of course, this is something that is not constant. But who has said that our elements has to be constants? They can be actually anything. So we construct a spring here with a changeable spring stiffness, you might say. So he will then take care of the dynamics in this problem. So yes, that is actually allowed. What will the bond graph here look like? Well, you have one rotating part, one moving part with its own unique velocity, rotational velocity. So yes, you start with the one junction. This one junction has mass attached to it. So you have an I element. And now we have added a spring instead of a source, which then was a little bit messy to include here. So I have my bond graph like this. That's it. And is it causal? Well, yes, of course it is. I would like the causal stroke here for the C element and here for the I element. And yes, for one junction, yes, this is the correct integral causal strokes, the way we like it. So now we can write our differential equations directly. Here you will have a P dot with a circle, and here P over I. While on this side you have Q dot, circle, and then Q over C. So there we have our bond graph now completely annotated. What is our differential equations here? Well, it's a second order system, and of course it is. We know that already, double derivative. So now we don't see a double derivative here, of course not, but we have two first order differential equations. Now first of all, a one junction, that is a common flow. And what is the flow? It's P over I, where we are missing the causal stroke. He is in charge. Hence, the flow has to be P over I. Q dot must then be P divided by I. So that's one equation. The other equation, what comes out must come in when you are talking about the effort. The sum of the effort has to be 0. And here I have two efforts, Q over C and P dot, both goes out, equal to 0. Hence I have P dot equal minus Q over C. So here is one equation, here is the other. Let's see if we get this one correctly. Let's see, do we need this one anymore? No, we don't need it. Let's rewrite them up here. P dot equals minus Q over C equals. Now this C we have here. So 1 over C. It will now be something like, what will it be? Minus yeah, mgl half sinus phi, and then we should have the q. Well, the q, that's the displacement, that's the angle phi, divided by phi. So of course this disappears, and we are left with this one. So here actually also you see the equation of motion. The change of the spin equals the torque that's attacking. So yes, this looks quite okay. Q dot equals P over I. Q dot equals P over I. So if you like here, you could just do a control, do a check, take the double derivative of this one, time derivative on each side, so then you will have Q double equals P dot over I, and then P dot divided by I, yes, you have it here already, equals minus mg L half sine phi by I. What is the the moment of inertia here, this I for a rotating rod. Normally you will find a table in an old mechanic book to find it. The moment of inertia here for a rotating object, well, by definition it was the integral of r square of all small masses included. So here you will actually have to do some calculations. Take some small element here, a small little dm, versus the distance from the rotating, the point of rotation. And if you do this, you should get something like, what will it be? The mass times length to the power 2 divided by 3 for this object. So that's something that we can hook up. Now let's try to do some programming. Actually, I have done that one already. Small little program. So here again I do it simple. Gravity is 1, length is 1, the mass is 1. The inertia, I use this formula here. M times L squared by 3. And then I have a P and then I have a Q. P and Q, what are these? Well, the P alone, that is the spin. So P, we don't have a P here anywhere. No. Remove this one. P, that is the spin. That is inertia multiplied with omega, or if you like, inertia multiplied with phi dot in a rotating world. So I start with the spin equal to 0, meaning no motion. He's just hanging still. But I give him an angle. And here I've started with quite a big angle, pi minus 1/2. So actually he starts up here. And then he starts to rotate, hopefully. So I have chosen here time step and maximum time. Calculating the P dot and the Q dot as we have them here. P dot equals this one. Q dot equals P over I. Update them and store them. Actually, I store only the position. I'm not interested in the rotational velocity. I'm only interested in actually the angle. I want to know this one as a function of time. So here I have calculated it and then switched from radians to degrees and then just plot them. So now let's see what happens. A little bit strange, isn't it? So you start with almost 180 degrees, start in there. And then he starts to swing back and forth, but then all of a sudden he goes too far. He sort of explodes. Why? He shouldn't do that. I think I've did some programming here just to show you what's going on. So that is the starting point, and now if you simulate, looks okay. Now we have no damping in the system, so he should continue like this forever. But what's going on here? Any explanation? I mean, we have solved this energy crisis in the world here. We have produced energy. What's going on? Let's crash him. Well, the reason is inside my first order Euler scheme here. It's not so accurate. Remember how we solve this? We calculate P dot and Q dot, and then we here say this is roughly the same as Q new minus Q old divided by delta T. This is a first order method. So finding the new one equals the old one plus delta T times whatever you have here. So it's a very simple procedure. If I do the simulation once more with a different time step, let's try one there. It shouldn't take too long, I hope. So now it seems to be okay. But if you continue, take a maximum time, a little bigger, then you see he explodes. So you can push him a little bit, yes, but now he exploded, say, after 200 seconds, and then he just starts to spin off. How can we remedy this? How can we remedy this? Well, we have to stop using a first order method, of course. Let's see, now we are back to the one where we started, yes. So let's try something else here. Instead of using first order Euler, let's start using ODE solver instead. ODE solver, what was the syntax? That was time and y equals, on the other side, ODE 45 of, and then we need a function. Well, we better make a function, say func, that's okay. And then we need a time span from 0 to max time. And then he needed the initial values. What was the initial values here? I started with 0, and then I had pi minus 0.5. So that should be the syntax for an ODE solver. Important here is the sequence of your initial data. The first one, that is 0, that was P. Second one, pi minus 0.5, that was Q. Okay, so this is my first equation. This is equation 1. This one is equation 2. So the sequence is decided here. So if you flip these two, okay, then you have changed the order of your equations. That's important. Because now we have to write a function. That should be possible. New script. Function. And then we need a name. DDT or something. Equals func. And here you have no choice, time, comma, y. Has to be like that. First of all, tell him what is this DDT. Well, that is two values, zeros, 2, 1. So that he know how many equations we're talking about. Then we have to calculate this one and this one, given that we know Q and P at any given time. Well, the P, that was the first one, so he will be handed to us by the first value of this y variable. Q, that's the second one. Like that. So now we can write our equations straight down. P dot, that was the first one we are going to return, DDT number 1, equals minus mass times G times L times sine of Q divided by 2. The second equation, that is simply P divided by I. P divided by I. That's it. But inside a function, you don't have access to all these parameters. So we have to tell him how he can find them. Where in memory can you find these? That you do with a global sentence. So I'm going to need mass, gravity, length, and the inertance. And the same global sentence has to be present in the main program. Save this one as a func. Go back to main. And here insert my global sentence. Down here we should now be able to plot t comma y. Will this work? Is it correct? Well, let's try. Let us comment out this one. Comment, and let's see what happens. Yeah, something is coming. Now what is what? And what are these numbers? Fancy shape on this, the first one. The first curve, that's the blue one. Well, my first equation, that was P dot. So the first actually is this spin, and frankly I'm not so interested in him. Second one, that is the position with given in angles, and here and then in radians. So we start close to pi minus 0.5. That's the initial state. But actually, I didn't want to plot the blue one, so I will remove him. So I just say colon, comma, number 2. Then I only get the angle. And now you see he will oscillate like he should, swinging around the initial angle back and forth, as he should. What happens if I now continue in time? Maximum time 500. Yeah, it works. 5,000. Yeah, still works. 50,000. Now he's working. Yeah, he can still handle it. You will actually also have problems with this system, but to see it you will have to starting angle very close to 180 degrees, almost straight up. So if you remove just a small angle here, then sooner or later he will also blow up, I think. You can still make it 5,000. Wow, he's really stable. Yeah, he actually can handle it. So that's impressive. I mean, in the earlier version of MATLAB, OD45 also exploded after have done several periods, because sooner or later he will go outside of the domain. I think they have improved the algorithm. So very good, very good. So no, you don't get any additional energy. Of course you don't. Any questions to that one? I'll put out these codes on the homepage so you can find them there. I haven't made much comments when it was this this graphical. So well, you can have a look at the code. I think you should be possible here to find out what's going on. It's a very nice way to create animations in MATLAB. You just modify the figure. You're changing the position for this rod in the time loop. Another possibility to create animation in MATLAB is remove this window and then print him as a new window every time, but that will not go so fast. It's also another option. Remove him by printing him again with white color and then print the new the rod again in the new position. But that's going to take forever. And MATLAB will then draw this problem slower and slower and slower. So no, it's a bad idea. But I'll put it out for you so you can have a look if you are interested. We will have more of these later on. We'll have more animations. So you will see how this can be done. A little bit time left, so I just take another cute little example. It's a fluid problem. We take a tube and we fill it with, say, water, like this. So initially you have filled this U-tube with water at a certain level, and of course we have gravity. And now if you give the water surface some offset, so say we have pushed this one down here at a certain position x, then of course he will pop up on the other side the same distance, because here I say the diameter for this pipe, the tube, is constant. How to model this one? How to model this one? Well, It's sort of a gravity problem here, isn't it? Gravity is the driving force here. But I will not start with including gravity in a source. Again, I will use the spring concept. So another way to think will then actually be reservoir, like this, and then a pipeline, and here then another reservoir. Sort of the same problem, but here drawn so that we sort of more easily can recognize what's going on. So yes, you have a tank on each side, liquid tank, which in bond graph world is a compliance element. It's a C element. So here I just say I have 2 storage tanks on each side. Very simple. And what is a C element? That was the area, surface area, divided by density and gravity. So you might say the gravity is already present inside the spring element. So don't add the gravity twice here by also think in terms of, oh, I need a source, I need a driving force into the problem. No, you don't. It's included in the spring already. For this liquid string, this one, you have an inertance, which then is given by rho length over area, like that. For the tube, we have a diameter d. So this one then should be a-okay. What will our bond graph look like? Well, you start with a one junction, because here you have a fluid string with one distinct velocity. True enough that he makes a 180-degree turn, but it's still one length of him, a constant length, with one single velocity. So we just start with a one junction. And this one junction, yes, he has a mass attached, an inertance attached to him. And then he branches. We will have a spring at each end, actually. So this will now be the bond graph. Okay, now we have 2 springs in parallel. If you are wondering how we should change this one or join this one together in one equivalent spring, how can we do that? Think of the mechanical problem. Here, spring, mass, spring, solid wall. And now, if you move this mass, say, back and forth somewhat, then of course you will have the effect from both springs at the same time. So what will the force be here? The force will be minus the displacement times k for one spring, but then exactly the same for the other one. So yes, you have 2 of the same springs. So we just double it. And of course this one we will now call an equivalent, no, not 2k equals k mark, an equivalent spring stiffness. So we do the same here. These 2 can be joined. So I will have the following bond graph, inertance, and just a C equivalent. And how to find him? Well, here you can add the spring stiffnesses directly, but remember the compliance, see, that's 1 over the spring. So we have the following equation: 1 over the equivalent compliance equals 1 over c plus 1 over c, then 2 over c. So he will actually be 1/2 of c. What about the equations? How can we find them? Well, we insert the causal strokes for the compliance. Should be here. Inertance should be here. So it's a second order system. And here we had P dot with a circle, P over I. Here we have Q dot circle, and on the other side Q over C. And our equations: one junction, common flow, Q dot equals P over I. While these two, they have to be added together to get 0, hence P dot equals minus Q over C. So there you have your 2 first order equations. Everybody agrees on that?
Will it be C prime or just C?
C prime, thank you. Thank you. C prime. This adjusted spring. What kind of equation is this? Okay, let's try to unravel it. I mean, these are the equations you will program. And what will you get out? You will get out the Q, which equals, what's Q here in the fluid world? Well, Q dot, that was the flow. So this is the volume flow, cubic meters per second. Q alone equals the volume. So the volume will now be x multiplied with the cross-sectional area of the pipe. P, well, P dot is the effort. So P alone, that's actually the time integral of pressure, dt, which is what? I have no idea, and I don't want to know. So the solution from this equation is not interesting at all. This one, there we have a physical explanation for it. So let's check it out. Take the first equation and take the time derivative of it. Then you will have Q double dot equals P derivative by I. And P derivative, we have an expression for him. He is negative. So this will now be Q divided by IC marked. So this is my second order differential equation. Okay. Insert the different constants here. What will it be? Q, that was the volume. So volume, that was displacement times the area, cross-sectional area. Inertance, we have here rho L over area. And the C marked, that was 1/2 of him. So that's area rho G, and then 1/2. Let's see, area falls, density falls, and 2 times gravity goes up. What do we have? 2 times gravity x area. by length, I think. Yeah, looks very good indeed. If you want to use x instead of q here, then this one will now be the volume double derivative, so it's x double dot multiplied with area. So only looking at x, it will actually be able to do, have dropped the minus somewhere. Should be negative. Minus, minus, minus 2 times g over L times x. So this is the equation. And yes, it's a linear equation describing a harmonic oscillation. And the natural frequency is just the square root of this part. Is it correct? Well, then you have to go back to the basic fluid mechanics and take a transient Bernoulli from this point along the streamline to this point, and then see, yes, you will indeed get the same equation. And you can actually see this frequency when the weather is bad. If you have a storm outside, or at least some strong wind, then you go and look down the toilet. In the toilet, you will have just this U-tube. So one is open. Here you can look down. On the other side, this goes all the way down to the sewer, but it's still open. So it's a water lock here. And this string, water string, will now start to oscillate. So then you can sort of check the frequency. Gravity is 10. The length is not that long, is it? Say 0.2, 20 centimeters. What will it be? The frequency omega is roughly square root 2 times gravity is 10 divided by the length 0.2. So this will be square root of 100, 10 seconds. So it should take 10 seconds for the liquid from top to go down and go up again. Just look next time we have some bad weather. Any questions? Then we stop here.